All right, so today we're going to look at 1.3. Okay, that's on segments and their measures. We're going to look at some formulas you've probably done before, like how you can take 2 points and find the distance between them. And we'll see, it's called the distance formula, but we'll see how that formula really is another formula that you probably learned a long time ago. All right, so first term I'm going to define is what's called a postulate. It's also known as an axiom. Yesterday I showed you 5 postulates, Euclid's postulates. A postulate is basically something that you accept as true. It's kind of a starting point, and you don't prove that it's true. Like in geometry, we would not prove 2 parallel lines never intersect. It's just, with the type of geometry we're doing, Euclidean geometry, that is something that's just assumed. Parallel lines never cross. Right? But if you see anything that has the word theorem, like Pythagorean theorem, that is something we have to prove that it's true, because it's a theorem. It's not, we can't just assume a squared plus b squared equals c squared, where a and b are your legs and c is the hypotenuse. We have to show why. But with a postulate, you don't. It's just a rule that's accepted without proof. And you need to have postulates in geometry, because if you didn't, you couldn't get anywhere. You can't prove every single thing. Otherwise, logically, you'd start to go in a circle. It's like if you looked up the word, depression in the dictionary, right? And you looked it up, and it said, like, to be sad. And then you look up sad, and then it said to not feel well. And then you look up, like, something like, you just eventually, if you keep looking up every word in a definition, you're going to go back into a circle to where you started, all right, eventually. So we need to have some things that we just accept. We don't have to prove them. They're just accepted without proof. If you have a rule that you need to prove, that's a theorem. Okay, and that's a big part of what geometry is that you don't do in algebra. In algebra, you don't really prove as many things. In geometry, we will. Which means in geometry there is a lot more writing than really calculations. We do some calculations, but a lot of what we do is about writing something out. Okay, and the first postulate we're going to look at in your book, it's called the ruler postulate. And the idea of the ruler postulate is a pretty simple idea. You probably just haven't ever thought of it this way. But it's that if you take all the points on a line, and obviously there's infinitely many points on a line, every single location on a line has a number that corresponds to that location. In other words, if I draw a line, and I want you to go to that spot right there, there is a specific number, and only one number, that represents that exact location right there. If I go to the right of that location a little bit, well, there's a way to get there too, but that's a different number, okay, or a different coordinate. So the idea is that every single point on a line has a number that represents its location. Okay? That's it. The number that represents the location we call a coordinate. Now, sometimes we have coordinates in one dimension, like just on a number line. Sometimes you have a coordinate in 2 dimensions when you're talking about XY axis. And what we'll do is we're going to start out really simple, just finding the distance between 2 points on a straight line. not even in 2D, just 1D, okay, on a number line. Okay, how would you find the distance between 2 points? If you had a point, at coordinate 1, you had another point at coordinate 6, how would you find out how far apart 1 and 6 are? What would you do with the two numbers? Yep.
Measure them, measure how far away they are.
Okay, what if you didn't have anything to measure with? How would you do that measurement as a calculation? All right, so if you have something at 1 and something at 6, you'd say they're 7 units apart? You could draw that out. 0, 6.
Count.
Okay, so for small numbers, you could just count how far apart 1 and 6 are. But what if you had points that were in the billions? They were billions apart. We don't want to have to count. We just want to be able to take the 2 points and do something with them, use a calculator if we need to find out how far apart they are. Yeah, Owen?
Subtract the 2.
Yeah, subtract the 2. So all you have to do is subtract them. Now, would we want to do 1 minus 6 or 6 minus 1?
6 minus 1.
Yeah, we want to make sure, because we're finding a distance, that it's positive. All right? And what could we do, though, in math to make sure, even if you did it the other way around, you did 1 minus 6 to get rid of the negative? Anybody remember what operation in math automatically makes a number positive all the time? Yeah, Connor?
Reciprocal.
No, not a reciprocal. That's a good guess, but that's when you flip a fraction. But there's something that automatically takes a number and always makes it positive. Yep.
An opposite sign.
Absolute value.
The absolute value, yeah. If you take the opposite of something, half of the time it would make it positive. If you already had something that was positive and you take the opposite of it, then it would make it negative. But absolute value is what always makes something positive. So all you got to do is subtract the 2 coordinates, and then take the absolute value. By taking the absolute value, it makes it so it doesn't matter what order you subtract the coordinates in. So technically, you could do A minus B, or you could do B minus A. Because of the absolute value, it won't matter. Okay. So I want to look at this notation that I just wrote down here carefully. I have an AB. Then later in the same statement, I have an AB with a bar over it. There's a difference. Okay? If you write AB like this, this means the length of AB. If you put AB with a bar over it, now you're talking about the actual segment. Okay? So one of these is talking about a numerical value about your object. This is the actual object itself. Like if you could pick it up, here's the object, here's the segment, here's the length of the segment. Okay, so any questions on that notation? Okay, so that's the notation you can use if you want to write the length of a segment. Just write the 2 letters, but don't put a bar or anything above it. Whenever you have 3 points on a line, okay, 3 points that are collinear, assuming they're all distinct points, you don't have points stacked on top of each other. One of your 3 points is always between the other 2. It has to happen, right? If you've got 3 points on a line, they're all distinct, one point is going to have to be between the other two. Again, we're just talking about collinear points, all on the same line. So that statement's going to lead us into our next postulate, which is called the segment addition postulate. Here's an example. I've got a line. I've got 3 points on it, A, B, and C, and B is in the middle. How could I find the length of segment AC if all I knew was the length of the first part of the segment, AB, and the second part of the segment, BC? I want the total length, but all I know are the two individual ones.
Add those two lengths together.
Add those two,
Lengths.
yes, add those two lengths together. Perfect. Okay. So in my diagram, I'm assuming B is between A and C, but you could do it any way you want. In this case, that's how it is. So there's a formula that would give you the length of AC. Take AB, that's the first part. Take BC, that's the second part. Add them together, and then you get the length of AC. Would it make sense if I wrote this equation with bars over each part?
Yeah. Wouldn't that be raised though?
Well, these are segments. AB is a segment, BC is a segment, AC is a segment.
Right, but technically if the line, you have opposite rays there. You have opposite rays right there.
Well, remember, if we're talking about a length, could we measure the length of a ray?
No.
No. So when we're dealing with lengths, we have to deal with just the segments here. True, BA is a ray, but we can't measure it because it just goes on forever. So we're just talking about the segments between those points. Okay, but my question was, if I put bars over AB, BC, and AC, would that make sense here?
Yes.
So when you don't put the bars, these all represent numbers. Taking AB, adding it to another number, and that's giving you another number. If you put the bars over it, now you're talking about the physical objects. It's not possible to add a physical object to a physical object. Okay, we can't do that. So if you want to talk specifically about things you can add, addition is something that applies to numbers, not objects. Okay? So that's why we don't want to put the bars over it, because we're not adding objects together here. We're adding the numbers together. Okay? The length of the object. Okay, so any question on that formula? Okay, and what if you wanted to find BC and all you knew was, say, this one and this one? What could you do there to get BC if you knew AC and AB? To kind of rearrange this a little bit. Dakota?
You subtract AB from AC.
Yeah, you could rewrite this formula. Here's another version of it. AC minus AB. Okay, so to find BC, you could take segment AC length and subtract segments AB, that length. Right, so you can rearrange this formula many different ways to find whatever length you needed. Right, now this is looking at the formula a little bit differently. It's kind of looking at it the other way. If I tell you that AB plus BC equals AC, if I guarantee you that that's true, then what that automatically means is B is the point that's between A and C. Okay? So you can look at this postulate in two different directions. If you know that B is between A and C, then this formula is true. Or, if you know the formula is true, then B is between A and C. Okay, what we just kind of did there, it's called a converse. And we're going to study that in chapter 2. It's basically when you switch the if and the then. Okay? And that's all I've done in the second part here. I basically switched the if and the then from the first part. Any question on that idea? All right, so let's look at kind of a simple example with it. It says use the map below. It's also in your book. They tell us that the distance from Albany to Macon is 90 miles, and then from Macon to Athens is 80 miles, and they want us to find the distance from Albany to Athens. Okay, so how would I write that out? Let's do it as an equation first, using the letters. I couldn't use A for Albany because I already had A for Athens. That's why I used B. But using the letters B, M, and A. What's the name of the length they're looking for? It's Albany to Athens, but it's what the length of which segment? Ian?
B to A.
Yeah, B to A. Or A to B. Same thing. Okay. And how would you get the length of segment BA? Katrina?
BM plus MA.
BM plus MA. Yep. That's exactly it. Okay. So now we're going to just do substitution with what we can to find the length of BA. Okay, how long is segment BM? About James, how long is segment BM?
90 miles.
Yep. So we're going to substitute in 90 for BM. And MA, Brian, how long is that segment?
80 miles.
80 miles. So we add them up. 90 miles plus 80 miles. Nick gives me 170. And the label we need on that? Miles. Yep. Okay, always make sure you put some kind of label on your answer if it needs one. Okay, in this case, miles. Any questions on that? All right, so that's using the segment addition postulate. We're going to see a very, very similar idea when we do angles, called the angle addition postulate. Okay, but today we're just doing segments. Okay, distance formula. So what the distance formula is basically used for is if you've got two coordinates and you want to know how far apart the segment is that connects them. Now we're specifically going to look at using the distance formula in a coordinate plane. There is a distance formula for 3D, and it's very similar to what you guys are going to do in 2D, but we don't do 3D yet. Okay, so we're going to deal in a plane, 2 dimensions, flat. Okay, and the formula it's kind of based on the Pythagorean theorem. And we'll take a look at how the distance formula comes from the Pythagorean theorem. Okay, how many people already know the Pythagorean theorem? Okay, if you know the Pythagorean theorem, then you already know the distance formula. Okay, and I'll show you how. So we're going to, in a second, we're going to draw a diagram with these 2 points, points A and B. And I'm giving A coordinate x1, y1. And when I talked about the ruler addition postulate, that kind of applied to a one-dimensional number line. Since I'm in 2D now, I need an x and a y value for my coordinate. Okay, so my first x, my first y, and then b, my second x, and my second y. let's sketch that out. Here's A. There's B. And I want to find out how far apart they are. Well, when you have a distance you have to measure on a diagonal, especially on a grid, that's not always easy to do. Okay? What kind of distance is easy to measure on a grid? You don't want, not one that's on an angle, but one that goes one of two ways. Yeah?
Up and down.
Up and down is very easy to measure on a grid. Yep.
And side to side.
Yeah, and horizontal. Okay. So what I'm going to do is I'm going to take this distance that I want to find, and I'm going to add in a couple segments. I'm going to add in a horizontal one. I'm going to add in a vertical one. Hey, what shape did I basically just create there? Yeah, I created a triangle. When I put that symbol in, does anybody know what kind of triangle that is specifically? Yeah, Sarah? That's a right triangle. And there's a formula having to do with right triangles that gives you a relationship between all the sides. And that's the Pythagorean theorem. Okay? So we're going to come back to that idea of the Pythagorean theorem in a second. First, I want to just find the distance of the bottom side. Okay? Since, let's see, this point and this point are perfectly horizontal. It's like they're on a number line. Okay? So the only coordinate that really matters to find the distance between A, let's call this one C, between A and C is the x values. What's the x value of point A? Yep.
That'd be 0.
Well, we don't have a
X value
number.
would be x1.
It would be x1, yep. And remember, to find a distance, we said earlier we need to subtract. Okay, so we have x1. And what about the x value of point C? It's a little tricky, but based on something that's above it and it's in a straight line with it, we do know the x value of point C, how far over it is. Yeah. Sure, go ahead.
X2.
Yeah, it's x2. Now, it doesn't matter if you do x1 minus x2 or x2 minus x1 because of the formula. Okay. You'll see in a second it won't matter. So that's the length of this bottom side. Just make sure you take the absolute value if you want to keep it positive. But again, when I plug it into this distance formula, you'll see why you don't need the absolute value. Okay, let's do the same thing to find the distance between B and C. Okay, let's start with C. Okay, what's the y value of point C? Again, it's not directly labeled, but it's in a horizontal line and it has the same height as another y value.
y1.
It's y1. It's at exactly the same y value as point A. And what about the y value of point B? How high up is that? So, Alyssa? Yeah, y2. So there's the height of our triangle. Okay, now we know the length of the base and we know the height. And as long as we know the Pythagorean theorem, we can use these two sides to find the length of the third side. Okay, what is the Pythagorean theorem? What is that formula, Denver? A squared plus b squared equals c squared. What's the A, the B, and the C? Okay, let's start with C. Which side is that? Well, yeah, in my diagram it was a point, but you gave me the letters A, B, and C, so I'm just using your letters. So what is the C normally represent in the Pythagorean theorem? No, not an angle. Yep.
Hypotenuse.
It's the hypotenuse. Okay, so it's the longest side. And then A and B are the shorter sides. Does anyone know the name of the shorter sides?
Adjacent and opposite. Well, that's for trig.
So, yeah, we could use terms adjacent and opposite. Those are used, as you said, more when we talk about trig ratios. But in general, the two shorter sides in a triangle are the, what do we call those? What, Tanner? You know what the shorter sides are called? The legs. Okay, the legs. So the two shorter sides, A and B, are the legs. C is the hypotenuse. Right? So all you have to do is fill in your lengths. Call that one A. Plug that in for B. And you basically have your distance formula. Okay? The only thing is that the Pythagorean theorem isn't giving you the length of the hypotenuse. It's giving you the length of the hypotenuse squared. So if we just wanted to know the length, not the length squared, what do you do to get rid of an exponent of 2? You take the square root. Okay? So you're going to see in the distance formula, there's a square root on each side. As I said, the order you subtract them in, x2 minus x1 or x1 minus x2, it doesn't matter because you're going to square it. Anytime you square something, it gets rid of the negative. Right, so we filled in the length of the base for A, square it, plus the length of the base, we filled that in for B. And we took this square root, as Denver said, because we don't want the length squared. We just want the length. Okay, so the distance formula is really just the Pythagorean theorem. It's the same formula. Okay, so what I'm going to do is put up a diagram, and I want to find the length of the segments in this diagram. Okay, it's three segments. Okay, I want to find all 3 lengths. And then I want to determine if any of the segments in that diagram have the same length. Okay, does everybody have the distance formula? Okay, so I'll make it a little bigger. Okay, so see if you can try that on your own. See if you can find the lengths of the 3 segments. You've got AB, we've got AD, and AC. Find those 3 lengths and then compare and see if any of them are the same. Okay, and we'll come back, we'll take a look at that in a second. All right, so let's take a look. Before we find the distances, what's a good thing to do that may help us out and speed it up a little bit? What should we label first? Oh, Olivia?
I have no idea.
Well, what do we need to know to find the distances? Like if I just wrote down on a piece of paper, said find the distance between A and B, and that's all I wrote. What do you need to know about A and B? Well, that's what I want to find, but what do I use to calculate that distance? That'd be a really bad test question if I just said, no diagram, no numbers, find the distance between A and B. I mean, what do you need to know that's used in the distance formula? Yeah?
You need to first draw right angles.
No, we don't need to draw any angles. But we do need to know.
We need to make like a triangle almost. That's what I did.
Okay, you can if you want. You could draw in those dotted lines like I did. That was more to just show you the connection with the Pythagorean theorem. But since we already have a formula now, we just need to know what to use that formula.
The coordinates.
The coordinates. You can't do this problem without knowing your coordinates. So the first thing I would do is write down all my coordinates. Okay, Jacob, what's the coordinate of D?
2.
Yep,
And 1.
2, -1. Okay, how about Eric, what's the coordinate of A?
1, 1.
So 1, 1 would be, that'd actually be quadrant 1.
It would be 1 negative, or negative 1, 1.
Yeah, first coordinate is always your x, you're going to the left. So it's -1, up 1. All right, and then B. How about Owen, what's my coordinate there?
Negative 5, 4, I think.
So -1, 2, -4.
Oh, negative 4.
And then up,
Oh, negative 4, 3.
-4, 3. All right, and C, that's 3, 2. All right, now we know all our locations, we can find our distances. All right, let's start with AB. All right, so we've got A is -1, 1. B is -4, 3. Right, so all we have to do is subtract them. It doesn't matter which one you let be x1 and which one is x2, but just do it the same when you do your y's. Okay. So we're going to have square root I like to just set that up so then all I have to do is fill in my numbers. Okay, so Tanner, what am I going to subtract in the first set of parentheses if I'm finding the distance between A and B? So this is your coordinate for A, and that's your coordinate for B. Sure. James, can you help him out?
What was the question?
I want to find that distance between A and B. So what goes in that first set of parentheses?
Negative 1.
Okay, so -1.
1.
Nope, not a 1. -1 minus. Okay, put in your x value minus your other x value. So we have -1 minus, what's my other x value?
Negative 4.
-4. Those are the two x values I'm working with for this part. Okay, and what about my y values? Brian, what will I subtract there?
3.
All right, so just make sure that we start with the same order we did in this one. So we decided to do -1 minus -4. So we'll start with the,
1.
yeah, minus 3. Okay, so now we do out the arithmetic and see what we get for a distance. What happens when you subtract a negative? Yep, you add it. So it becomes -1 plus 4, which is how much? 3. So 3 squared. 1 minus 3 is -2 squared. 3 squared is 9. -2 squared. Nick, what's that? 4. And we get the square root of 13. Okay, so that's the length between A and B. Anybody get square root of 13 for that? Okay, good. If they don't ask you for a decimal, there's no reason to plug that in and round it off. Okay? So we don't need the decimal for that. All right, now we'll do A and C. Set up our formula. And just fill in the 4 numbers in the right spots. All right, so now we're using -1, 1, and 3, 2. Those are my numbers. Okay, so Ariel, what's my first x value? using those two coordinates? Sure, could do -1 minus, and what's my other x value? 3. Very good. Okay, and my y value? Yep, 1, and my other one? 2. 1, 2. Now simplify it, see what we got. Okay, -1 minus 3. Olivia, what's -1 minus 3?
-4.
Yep. -4 squared plus, Owen, what's 1 minus 2?
-3.
That'd be -1 minus 2. That'd be -3. So it's +1, take away 2.
-1.
Yeah, -1. Okay, and we need to square it. -4 times -4, that's 16. -1 times -1 is 1. So I get the square root of 17. So what can we say about the length of AB and the length of AC?
Same.
They're not the same. So AB and AC, not the same. Okay, let's finish up with AB. Okay, so this time we've got -1, 1. I'm going to use this coordinate and that coordinate. All right, so let's do -1 minus 2 squared. Those are my x's. And now do the y's. 1 minus -1. All right, Dakota, what's -1 minus 2? -3 and squared? 9. Plus, okay, how about Justin? 1 minus -1. 2 squared gives me 4. And we get the square root of 13. Okay, so we go back and look at it. We had another segment that had the length of 13. So how would I write down which two segments have the same length? Which two? Yeah.
Segment AD and AC.
AB and
AC and AD. No, AB and AC.
AB and AD. Those are the two segments with the same length. AB and AD. Yeah.
Segment AB is equal to AD.
Yeah, so there's a couple, I think I mentioned this on the next page. You can write down that the measure of AB equals the measure of AD. If you want to put the bars over it, we need to use a different symbol in between these two. And I'll show you what that symbol is. If two segments have the same length, there's another word that we can use to describe that. It's called congruent. Okay, so I've drawn two segments up above, AB and CD, and I tried to draw them so that they're the same length. Okay, they are congruent. That's the symbol for congruence. It's an equal sign, and it's got kind of a wavy curve on top of it. Right, so if you want to say that segments are congruent, this is the symbol that you use. A congruent symbol does not apply to numbers. That doesn't make sense. A congruent symbol applies to the actual object itself, the segment. Okay? So AB, segment AB is congruent to segment CD, meaning if two segments are congruent, then it means their lengths are equal. That's what I've written on the right-hand side. So an equality sign is used with numbers. Here, AB is a number, CD is a number. These are lengths. these are the actual segments themselves. Okay, so any question on when you'd use a equality sign or when you'd use a congruent symbol? Yep.
Well, I have more of a question. Would you accept both, like either one on a test?
It just depends what I'm asking for. If I ask you on a test to say which segments are congruent, okay, I would be looking for you to say something with a congruent symbol. If I asked you write down the lengths that are equal to each other, then I'd be looking for something more like on the right
But
side.
if it doesn't classify, you would accept both, or either one?
Yeah, but I'll specify so it's clear. Yeah. Any other question about the difference between an equality sign, which is used with numbers, and a congruent symbol, which is used with the actual segment itself? Okay, so something we could say now on this page, if it asks, tell which segments are congruent, we could write this. Segment AB is congruent to segment AB. All right, so the last one we'll do, down below it shows a grid which represents a map of city blocks. The east-west blocks, which is the distance between two vertical grid lines, so from east to west, they're 380 feet apart. The north-south blocks are 480 feet apart. Okay, so two questions. First one is, I want to find the walking distance between A and B. Okay, so if you were going to walk from A to B, and you're doing it on the streets, how do you have to walk? You can't, how would you have to do it?
Well, the shortest distance between 2 points is the line. So you would have to walk in a straight line to your destination.
Would that be possible, though, necessarily in like a city?
In like a city, no, because there would be buildings.
Right. So for the walking distance, I want you to walk on streets. Okay? Let's pretend that between here there's buildings and we can't just walk straight. All right? So the walking distance is, well, there's two ways to go. You can either go right and then up, or up and then right. It's going to come out the same. Okay, so that's the first thing I want you to find, the walking distance. And then if there was a street that ran diagonally, okay, between the 2 points, I want to find what that distance would be. Okay, so the first distance, and then find the second distance. Okay, so try that. If you need a calculator, I'll get those.
What's the distance again for up and down?
The up and down, 480. So each block that you walk up is 480. Each block that you walk over is 380. Okay. Try to find the walking distance, and then if there was a street connecting them, find that distance.
We got that. So 480.
All right, so let's start with the first part. Okay, what I would do to find the walking distance is first just count how many east-west blocks you need to go. So you need to go 1, 2, 3, 4, 5. So you got 5 east-west blocks, and each one of them is 380. And then for north-south, do the same thing. You got 1, 2, 3 north-south blocks, and they're 480. Okay, so 5 times 380 gives us 1900 plus 480 times 3, that's 1440. Add them up. 2,340 feet. That's how you do the first part. Okay, the second part has to do with the distance formula. Okay, so if you're going to use the distance formula, you'd need the coordinates of these points. Well, you've gone over to the left 2 east-west blocks and down 1 north-south. So if you do that out, the coordinates come out to negative 680, negative 480. Okay, for B, you've gone right 3 north, east-west, and up 2 north-south. So if you do that out, it comes to 1,020, comma 960. And now, once you have the coordinates, you just use your distance formula. The numbers are much bigger than the problem we did before, but it's the same idea. Just use your distance formula to find that. Which distance would be shorter? The straight line distance or walking on the city streets? Yeah.
Straight line.
Yeah, the straight line distance is always shorter. Okay? So we'll look at some more problems like that in the homework. Okay, so the homework is on pages 21 to 23. Okay, it's all odds. 1 through 11 odd, 21 to 27 odd, 31, 35, 39, 43, and 47. It's all odds.